Hi everyone! Today let's talk about the last case, one repeated root, when we want to solve the system of linear ODEs with constant coefficients. Okay, so from chapter 6, when we talk about the eigenvalues and eigenvectors, so in the case of one repeated root, sometimes there are two linearly independent eigenvectors for a repeated eigenvalues. So here we are talking about the 2x2 matrix case, okay? Sometimes we can have two linearly independent eigenvectors for a repeated eigenvalue, and then the work is done, okay? And other times there is only one linearly independent eigenvector, then we need to look for another solution of a different form. Okay, so let's look at example 5. So we want to solve the initial value problem system. So let x be x1, x2. Then this guy is the same as x prime is 3x1 and 3x2. Okay, so this is the matrix A. Well, here, this is the matrix A. What's the first step? We compute the characteristic equation, right? We subtract lambda from the diagonal elements, and the rest is zeros. Okay? Oops, sorry. The determinant of that. So cross multiply, we have 3 minus lambda squared and minus 0. Wow, we set it equal to 0, we get lambda equals 3, and it's a repeated root with multiplicity 2. So far, so good. Yeah, so this is the eigenvalue. You can see we only have one eigenvalue. Okay, so for that eigenvalue, let V be xy. We need to solve A minus lambda I times V is 0. What is the arithmetic coefficient matrix? So A minus lambda, so 3 minus 3, 0, 0, 0, 0, 0. Ooh, everything's 0. What does that mean? Remember, this is x, this is y. They're all 0. It means they are actually free. Okay, so they are free. It means V is then xy, so we can think about x 1 0 and y 0 1. Yeah, the coefficient of x is 1 0 and the coefficient of y is 0 1. So here we have, so those will contribute to so those are both the eigenvectors. See, we have two eigenvectors associated with the eigenvalue 3. Then what is the solution? Well, the solution is C1, the first eigenvector, e to the that eigenvalue times t, right? E to the 3t plus C2, the second eigenvector, 0, 1, and then e to that eigenvalue times t. Okay? Because we have two eigenvectors, so solutions look like that. So far, so good, everybody. And we can also solve for the coefficients C1 and C2 because here x1 and x2 they're all 1. So we plug in x of 0 is 1, 1. Okay, so we plug in t is 0, we get C1 1 0 plus C2 0 1. Oh, so we have both C1 and C2 just 1, right? So that's why we have C1 is 1, C2 is 1. And then our solution is then C1 is 1, so we have 1 0 e to the 3t and plus C2 is 1 0 1 e to the 3t. So this is a solution to the system of linear differential equation with constant coefficients. So far, so good? Yeah, so you can see if we have one eigenvalue, if we have two eigenvectors, then the way how we set up the general solution is the same as before. It's the same like the case when we have two real roots, right? We use the eigenvector times e to that corresponding eigenvalue times t. Okay? So, but what happen if we have only one eigenvector to that associated with that eigenvalue? Okay, so let's look at example 6. So example 6, solve the system with a equals to -5, -3, 3, 1. Alright, so the first steps, we also compute the characteristic equation. So we subtract lambda from the diagonal elements, and the rest entries stay the same. So cross multiply, but we subtract, right? So -5 minus lambda times 1 minus lambda, we subtract -3 times 3. -5 times 1, -5. -5 times minus lambda plus 5 lambda. Negative lambda times 1, negative lambda. Negative lambda times negative lambda. Positive lambda squared. Minus negative become positive 9. Let's reorder it. So we have lambda squared. 5 lambda minus lambda is 4 lambda. 9 minus 5 is 4. Ooh, can you see this is actually the complete square of lambda plus 2? So we get lambda equals -2 is the eigenvalue. And is it repeated with multiplicity 2? So far, so good, everybody. So for that eigenvalue, what is the eigenvector? Well, we want to solve a minus lambda I times v is 0, right? And what is a minus lambda I? Well, we subtract lambda from the diagonal. So -5 minus 2 is -7. 3 stay here. Then we have -3 here, right? So, sorry. Lambda is -2. So -5 minus -2 is -3. And then 1 minus -2 is 1 plus 2, that's 3. Oh, you can see the second row is always the multiple of this first row, so we can use -1 add to row 2. -3, 3, 0, 0, 0, 0. So we always get the last row zeros. So this is x, this is y. -3x plus 3y is 0. Then x is y. Yes, so v is x is y, so we have y and y. We can pick y to be 1. Then v is then 1, 1. So we find an eigenvector. Well, but there's only one eigenvector, right? So we know one of the solution. So we know one of the solution is C1. Is C1 the eigenvector 1, 1 times e to the what is that? -2t. So this is one of the solution. But however, we only have one eigenvector. We can only get one solution. So we need to find a second solution so that it can generate the solution space. So how do we find the second solution? All right. Do you remember in chapter 5? Do you remember in chapter 5, when you have two real roots, your solution is, so if you have two real roots, your, let's say, R1 and R2, your solution is like C1 e to the R1x plus C2 e to the R2x, right? If you have a repeated root R, your solution is y is C1 e to the Rx plus C2x e to the Rx, right? You multiply by x for that solution to get the second solution. So based on the analogy with the single equation case, we try the second solution. Sorry, abuse of notation. So this means the second solution. Maybe I should put my notation to be x2. So that denotes the second solution. Okay, maybe we can try to multiply the first solution by t to get the second solution. Okay, because we do that in the single equation case, right? Okay, so let's try that. So let's plug into the this differential equation. X prime. What's x prime? Well, x prime is then, well, here, because we have, what is that? Product. So we need product rule is the derivative of the first guy. So Vt derivative is just V, because the t derivative of t is 1, times the second guy plus the first guy times the derivative of the second guy. Well, the derivative of e to the lambda t is lambda e to the lambda t. So that's why when you plug into the differential equation, you get, this is your left hand side. V e to the lambda t plus lambda v t e to the lambda t. And your right hand side is a times x. X is v t e to the lambda t. So because we can divide it by e to the lambda t on both sides, e to the lambda t is never 0, so we can do that. Well, after we divide it by it, we have v plus lambda vt equals to a vt. Well, but this will not work because there's no term on the right hand side. Oops. Did I press anything? There's no term on the right hand side to balance with the v term. See, we look at we can see here, we look at the constant term, right? The constant term, we have v here, but we don't have a constant term here. But and the t, we have the with the terms with the t. So the t term we have good, but the constant term, we don't have a term on the right hand side to balance with the v. So this won't work. So it's okay. We just need a constant term here. So what will make this constant term? Remember your setup for x2. We have vt e to the lambda t, but just add a lower order term. Okay? So instead of just a single term of this, we need to plus a lower term. A lower term is u e to the lambda t. So we don't call it v again. Let it be another vector u. Let's call it u. Okay, so now, what is the derivative? So let's plug into our differential equation again. So what's the derivative? Well, here is product rule. The derivative of first guy is just v e to the lambda t plus vt. By the way, the product rule for vector is the same as a single variable, right? Single dimension. Okay, so derivative of e to the lambda t is lambda e to the lambda t. Derivative, so u is constant, put it down. Derivative of e to the lambda t is lambda e to the lambda t. So plug this on the left hand side. And the right hand side, we have a times x. So a times vt e to the lambda t plus a times u e to the lambda t. Okay, now let's match the terms. Let's look at the terms. Let's look at the coefficient of the terms. E to the lambda. Well, the e to the lambda term. So here, this guy and this guy and this guy. So we have v plus lambda u equals to au. Alright, next, let's compare the t times e to the lambda t term. Okay, so on the left hand side, we have lambda vt. On the right hand side, we have avt. So the coefficient is av equals to lambda v. Okay, so the method we're doing here is very similar to what we have done in section 5.5 when we use the undetermined coefficient to solve the non-homogeneous differential equations. Okay, so we also differentiate it and put it back into the differential equation, and then we compare each terms. And we compare the coefficients and solve the constants, right? Okay, now let's look at equation 2. Equation 2, what does that tell us? Well, it tells us that AV minus lambda V is 0. Ooh, that means lambda. So that means V is the eigenvector associated to the eigenvalue lambda. Well, that is exactly the V we find, right? Remember, in that case, we find one eigenvector for that eigenvalue lambda. Okay, so we already find V. V is, in fact, the eigenvector that match with our result. That's good. But that the first equation, what's the first equation means? Well, the first equation, let me move lambda u on the other side. We get V is then AU minus lambda u, right? I can then factor out the u. Then we get A minus lambda I times u. I can view lambda u as lambda I times u. Right? So that means how can we find the u? You solve the system A minus lambda I times u equals to V. Okay, so summary. For a repeated eigenvalue with only one eigenvector, what do? Okay, first, find the eigenvalue and one eigenvector just like what we did before. Second, to find the second solution to the solution, okay, general solution, you're gonna set A minus lambda I times u equals to that V, the eigenvector you found in the previous steps. Okay, and then you solve for u. Sorry, typo. Okay, and then our second solution, alright, okay, second solution, my notation is x2. Okay. My second solution is gonna be vt e to the lambda t plus u e to the lambda t. Alright, then the general solution is our C1 times the first solution plus C2 times the second solution. See, now we get two solutions to generate the solution space. So far, so good, everybody. Let's continue. So last time, let's recall. Okay, so let's recall. This is our Okay, so sometimes people don't put the C1, they let this guy be the first solution. Okay, and then the general solution is the linear combination of the solution, the first and second solution. Okay, so we get the eigenvalue. So the eigenvalue lambda is -2, and the eigenvector V is 1, 1. To find the U, what do we do? Okay, so we call them the third steps. Okay, so to find the U, okay, it keeps deleting my stuff. So let me see. It can work now. All right. Yeah, sometimes when Word documents freeze or delete my stuff. Alright, so we want to set up A minus lambda I U equals to V. So what is that? What is A minus lambda I? Well, let's go back. Okay, so this is our A, right? This is our A minus lambda. So we subtract lambda from the diagonal elements, -5 minus -2. So -5 plus 2 is -3. And then we have 3. Don't delete my -3. It keeps deleting my stuff. Okay. let me slow down and see whether it works. Okay, -3 and here 3. Okay, but on the right hand side, see, it's not 0 anymore. It's the eigenvector we found in the previous steps. Okay, so that's the difference. Let me highlight it with yellow. Okay, the right hand side is not 0 anymore. It's the previous eigenvector you found. Okay, let's continue. Can you see the first row is the same as the second row? Yeah. Let's use negative row 1 add to row 2. Okay. So -3, 3, 1, 0, 0, 0. So we see this is by the way, what's u? You let u be x, y. Then this is x, this is y, this is the right hand side. Okay, what's that mean? Well, -3x plus 3y equals 1. Okay, so x is then, let's see, we can move the -3 on the other side. It's going to be 3y minus 1 divided by 3. So we get y minus 1 over 3. So far, so good, everybody? Okay, so we get u is then xy, x is y minus 1 over 3y. Okay, and then so here you can see you can plug in the y value to be anything, right? So in fact here you can pick y to be any number including the 0. So u is then when we plug 0 we get minus 1 over 3 and 0. Okay, everybody? So our second solution is v t e to the lambda t. V is 1, 1. T e to the lambda is -2t plus u is -1/3 0. Okay, and we get e to the -2t as well. Okay, so let's see. So our general solution is C1, X1. X1 is 1, 1, e to the -2t plus C2. Our second solution is 1, 1, t, e to the -2t plus -1 over 3, 0, e to the -2t. Okay, so now I want you to look at this guy. So here we pick y is 0, right? Well, what happens if we pick y is 1? Well, you can think about if we pick y is 1, it's kind of like you use this guy to add this guy. Okay, because the C1 can be any number. So if you pick y is 1, it's kind of you add this one. Okay, oops. Okay, so we use this one to subtract the negative, to subtract 1/3, and we use this one to add the 0 here. So we will still get the same answer. Okay, so that's why to find the u, you can pick your y to be 0. But when you find your eigenvector, you cannot pick your y to be 0. So far, so good, everybody. Okay, oops, sorry, erase that by mistake. Okay, so do we have initial condition for this problem? Okay, no, we don't have initial condition. Then this is our final answer. Okay, so this is our final answer to this problem. So we have found two solutions to generate the solution space. Okay, so that's why you can compare all the cases. If we have one repeated root, but you can only find one eigenvector, well, then you have to show more work to find the second linearly independent solution. Okay? All right. Now, let's see here. What's next? Let's look at some application problems. So the application problem. So here we have the chemical solution. Alright, so the amount x1 of T and x2 of T of salts in the two brine tanks satisfy the differential equation. The rate of change of the x1, so x1 is the amount of salt in the first tank, and x2 is the amount of salt in the second tank. Okay, and you can see the water is flowing at a rate of r gallon per minute or cubic meters per hour, something like that, right? So what's the rate of change? Well, the rate of change of the amount of salts is when you get in the water, you're getting more water, but you're not getting more salts, right? But when the solution is flowing out, you're losing some salts. So what's the amount of salt you lose? Because you lose, so you get negative. And that you lose, the amount is proportional to the amount of salt in the tank. What is the proportion? Well, that is the amount of the liquids that you're losing over the volume of the tank. Okay, so that's why K1 is R over V1. So that's amount of salt you lose. And let's look at the second tank. You gain some salt. So the amount of salt you gain is K1 times X1. Okay. So it's the proportion, which is R over V1 times the amount of salt in the first tank. And you're also losing some salt. What's the amount of that? Is K2. So that is the proportion of the amount of salt in the tank 2. Okay, so K2 is R over V1. So that's why we get this systems of differential equations. And they're linear with constant coefficients. So we can use the technique we learned before to solve it. Okay, let's see our example 7. Okay. So suppose V1 is 50 gallon, V2 is 25 gallons, R is 10 gallons per minute. X1 of 0 is 15 pounds of salt, X2 of 0 is 0 pounds of salt. Oh, so it has no salt initially. Solve for X1 of T and X2 of T. So let's plug in the numbers. We have X1 prime is negative K1. K1 is R. R is 10 over V1. V1 is 50 X1. And X2 prime is K. So positive of K1 X1. So whatever we get on top, we make it positive. Minus K2. K2 is R over V2. V2 is 25 X2. Well, this is the same as minus 1 over 5 x1. This is 1 over 5 x1 minus 2 over 5 x2. So far, so good, everybody? Alright, so let's call V be x1, x2. Well, then this guy is the same as x prime is the matrix negative 1 over 5 x1 but 0 x2. 1 over 5 x1 and negative 2 over 5 x2. So this is our matrix A. Okay, so after we get the matrix A, what do? How do we solve it? Oh, we look at the characteristic equation. A minus lambda I, so we subtract lambda from the diagonal element. And the other entries stay the same. Okay, so cross multiply but negative. Minus 0. Ooh, nice. So when we set this guy 0 is, we just set each factor equals 0. Okay, so this guy we have lambda is negative 1 over 5. Here we have lambda is negative 2 over 5. So we have 2 eigen value. So far so good, everybody? Alright, let's continue. And for each of the eigenvalue, let's figure out the eigenvector. So for lambda equals negative 1 over 5, let V be xy, and we want to solve A minus lambda I, V equals 0. Alright, what is the augmented coefficient matrix? A minus lambda I, so minus 1/5 plus 1/5, 0. Oh, 1/5 minus 2/5 minus negative 1/5, that's 1/5. Oh, I can swap row 1 and row 2, and I don't like fractions, so I multiply by 5 after the result. So I do 2 steps here, then I get 1, 1, 0, 0, 0, 0. So far so good, everybody? Alright. Oh, sorry, I make a mistake. So negative 2/5 minus negative 1/5 is minus 2/5 plus 1/5 is still negative. Okay, so this is negative. Yeah, it's very important to check our work. So that's x, that's y. This is the right hand side. So we have x minus y is 0. X equals y. So v is then y. We can take y is 1. Then our v becomes 1, 1. That is the eigenvector. Okay? And for the second one, let's continue. When lambda equals negative 2 over 5, what is A minus lambda? Well, minus 1/5 plus 2/5 is 1/5, and we have 0. And 1/5 minus 2/5 plus 2/5, 0. Oh, okay. You see here, they're the same. So minus row 1 add to row 2. We get 1/5, 0, 0, 0, 0, 0. This is x, this is y, this is the right hand side. So the first row tells us that 1/5 x is 0. Ooh, x is 0. So y is 3, then v is 0y. Okay, so we can pick y to be 1, then v is 0, 1. This is the eigenvector. Okay, so now we have find 2 eigenvalues, and each eigenvalues we can find an eigenvector. So we can set up the general solution is C1, the first eigenvector, 1, 1, corresponding the eigenvalue negative 1/5 t. C2, the eigenvector is 0, 1, the corresponding eigenvalue negative 2/5 t. Alright, so that is our solution, but because we have initial condition, x1 is 15, x2 is 0. Okay, so we plug in 15 and 0. Let's see, when we plug in t is 0, we get C1, 1, 1, e to the 0 is 1. C2, 0, 1, e to the 0 is 1. Oh, let's look at the first row. First row tells us C1 is 15. Second row, C1 plus C2 is 0. So C2 is minus 15. So our solution, x of t is C1. C1 is 15. 1, 1, e to the minus 1/5 t. Plus C2. C2 is negative 15. 0, 1, e to the minus 2 over 5t. But what is the problem asking? The problem is asking, let me copy here because I don't want to go back and forth. So it's asking x1 of t and x2 of t. So what is x1 of t and x2 of t? Well then, oh, don't reorder it. Okay. So x1 of t is, you look at the first row, right? The first row corresponds to x1 of t. Well, that's 15 times 1 e to the minus 1/5 t, and then 15 times 0, 0. So that's x1. Well, x2 is then the second row. So 15 e to the minus 1/5 t minus 15 times 1. So 15 e to the negative 2 over 5t. So far, so good, everybody? Okay, so that is x1 and x2. And then, part B. Find the maximum amount of salts ever in tank 2. What does that mean? Well, maximum amount. From calculus 1, how do you find maximum? Well, you differentiate and set the derivative equal to 0 to find maximum and minimum, right? You find the critical point, so we tend to, so x2, let's differentiate it. 15 minus 1/5 e to the minus 1/5 t minus 15 minus 2/5 e to the minus 2/5 t. What is that? Well, that's negative 3 e to the minus 1/5 t minus minus become plus 6 e to the minus 2/5 t. Okay, so here it's better to factor. So factor completely. Well, you can think of this guy is e to the minus 1/5 t times e to the minus 1/5 t. So we can see the common factor. Well, the common factor is then 3 e to the minus 1/5 t. That's the common factor. So I have minus 1 and plus 2 e to the negative 1/5 t. Is that okay, everybody? To find the critical point, you set it equals 0. By the way, this guy is always positive. Exponential function is always positive. So the only case make this guy 0 is when this factor is 0. So minus 1 plus 2 e to the minus 1/5 t is 0. Solve for t, move the 1 to the other side, and divide it by 2, we get e to the minus 1/5 t is 1/2. Let's take ln on both sides. So minus 1/5 t is ln of 1/2. And that's the same as ln of 2 to the minus 1. That's the same as minus ln of 2. Then you can see, multiply both sides by minus 5. We get 5 ln of 2. Okay, so this is the critical point. Once you find a critical point, what do? You also need to find a domain. Well, the domain for t is between 0 and infinity, right? Let's draw the picture. So 0 here, infinity, 5 ln of 2 is right here. So x2 prime and x2. Okay, this is the critical point we know is 0. So pick a number in here. Let's pick 0. Let's plug into our x prime. So let's plug into x prime. Where x prime is right here. Okay, we want to plug in here. So you plug in 0. E to the 0 is 0. So minus 1 plus 2 is 1. Oh, so we have positive. And here, think about it, if t is getting to infinity, well, minus e to the negative 150 is going to be very, very small, getting close to 0. So then the minus 1 will dominate. So the answer is going to be negative. So if the derivative is positive, then the function is increasing. If the derivative is negative, then the function is decreasing. So we in fact have some maximum here. Yay! That's matched with our questions, right? We want to find the maximum amount of the salt ever. So the maximum amount of salt happen when the time is 5 ln of 2. Well, let's plug it into our functions. Our function is right here. Okay, so let me see whether I can copy it. So, okay, maybe I don't need to. So 15 e to the minus 150 minus 15 e to the minus. Okay, so 15 e to the minus 150. T is 5 ln of 2. Minus 15 e to the minus 250. T is 5 ln of 2. Let's see what is that. Okay, so 15, 5 cancel. This is the same as e to the ln of 2 to the minus 1. Yeah, we can move the minus 1 on top of the 2. And then here we have 5 cancel. It's the same as ln of 2 to the negative 2. We can move the negative 2 on top of the 2. So then e and ln cancel. We have 15 times 2 to the negative 2 is the same as 15 over 2 minus 15 over e and ln cancel. E to the 2 to the negative 2 is the same as 1 over 4. Oh, so that is 15 over 4. Well, 15 over 4 is like 3.75 pounds. So that is the maximum amount of salt ever in tank 2. How about tank 1? Well, tank 1, because this guy, tank 1 is exponential function, because it's e to the negative, is a decreasing function. It's just losing, you just keep losing the slots forever, right? So, and it makes sense because, don't forget our picture. You see our picture, you're adding water and then you're losing your solution. So the amount of salt in tank 1 is actually, you're losing it. Okay, but the tank 2, you're adding some salt, you're losing some salt, so we don't know. But actually we can solve it and we can find the maximum time, the maximum salt ever is when the time is 5 ln of 2 minutes. Okay, so that is this application problem. So you can also have other type of application problems like the spraying, like the beginning of this session. We talk about the spraying, and this is but the spraying is the second derivative, so you won't see the second derivative in your final exam. But like a problem in your practice exam. Okay, so you can have a problem like this in your practice exam as well. Okay, so that's it for this session, and this is the last session in our course. Okay, so I will miss you a lot, and on the office hours we were gonna make a review, and I can answer your questions. All right, see you. Bye.